I'm August Noevere, Director of Research, and I'll be presenting on HyperX CAD and Composites digital thread. So I'll be sharing an update today on our capabilities to interface with external CAD and Composites tools. About 2 years ago at the last users conference, I shared kind of our initial work in this area. Since then, we've added a lot of exciting new things to this digital thread topic based on feedback from customers, you guys, and incorporated some new things, which I'll be covering in this presentation. So why is the CAD and Composites digital thread important for HyperX? So it's been touched on a little bit in prior presentations, but kind of despite all of the advancements in modeling and simulation tools, engineers still often find themselves sharing data with colleagues back and forth through PowerPoints, Excel files, email, screenshots, those kinds of things. This approach is obviously inefficient, error-prone, and difficult to track formally through some kind of PLM process. So as many of you probably know, a lot of software providers are addressing this challenge by integrating tools from multiple disciplines all within one single product. But even so, the reality is that many engineering teams are still working with software from multiple vendors, which can we still have that challenge of trying to find a common ground of how we exchange data. So with HyperX, we're trying to kind of find a middle ground where we're passing data back and forth with other disciplines, exchanging data with other disciplines through standard CAD file formats. Trying to support, our goal is to support as many different formats and types of data or CAD data features as possible. So when HyperX user needs to interface with a CAD user, the idea is that they would do that directly through CAD files, which is obviously a lot more streamlined. It's also something you can track directly in a PLM system if it's just a single CAD file that has all your data that's either going to or from HyperX. All right, so now that I've introduced the topic, quick outline. I'll start with sort of telling that story with CAD topics. I've got a few intro slides, and then a demo video that we'll just kind of watch and go. I'll talk to demonstration of the software, and then I'll tell sort of the same story for composites topics as well. Talk about new features, still digital thread related, but in the composites world specifically. All right, so starting with the CAD workflow. I'll use this to kind of set up the CAD exchange story. So on this flowchart at the top, we've got the CAD import or CAD import from your native CAD tools into HyperX, and on the right side is the CAD export. So starting with the import, kind of the idea there is we want to enable HyperX users to kind of consume the current state of the CAD design. As most of you probably know, that the evolution of the FEM kind of lags behind the evolution of the CAD model, so you may have a need to sort of consume design data that's not yet in the FEM you're working with. And other times there's features in the CAD model that are not even represented in the GFEM. You need to be able to understand them, get dimensions off of them, and update your analysis accordingly. So for the CAD import, some of the new things that we've added in this upcoming release. I forget to mention anything in green text is kind of a new upcoming feature in the June/July release. So for import, we've added a whole bunch of new formats, several for supporting Siemens NX, so kind of standard CAD formats, as well as you can directly import the Siemens NX part file.
I'm sorry, August, I just wondered, could you list those off that it's actually marked by the podium?
Oh, all right, will do. So yeah, at the top, STEP and IGES formats, which we've supported for a while. Of course, that can be used with any software just about. Then we've got the JT format, which is, I believe, NX specific, or there might be a plugin for CATIA as well to support JT. That's a new format. Then we've got the Siemens NX part file, Parasolid formats, which is also, I think, mostly Siemens specific, and then a CAT part file as well for the CATIA users in the room. So that's import. For export, there's a few things we've added as well. So last time at the users conference, I showed the stiffener geometry generation and export. And there's a few things we've added as well. So this may look suspiciously familiar to something Paul mentioned in his presentation, but we've added basically metadata or annotations that can now be exported into a CAD file, JT or STEP specifically. And then we've added a few new features in the composite ply data export, which I'll show in a little bit. All right, so moving on to the first demo here. Hopefully this is a video. The first few seconds are freeze frame, so I think it's playing. Yeah, there we go. So the first I'll show the CAD import from a CAD tool into HyperX, and there's the table of formats again. So here we are in the HyperX interface. We've got a CAD model that's been imported. This is supposed to be like an example of your current structure assembly. These parts are all solid bodies. We've got the imported CAD in the viewport, and then we also have it stored in the tree. You can organize it into folders however you choose. This example has things like fasteners in it. That was kind of quick. Fasteners, as I mentioned, that's all solid parts, things with flanges and cutouts and all those types of features we're used to seeing on detailed CAD models. So one of the first things you might do here is just overlay your CAD model with your FEM and try to maybe uncover, like I mentioned earlier, things that are on the CAD that you need to be aware of when you analyze. So moving on to new features, the first one here is the measuring tool, which is being used in this case to measure spacing between fasteners. So measuring is not a particularly exciting topic, but it is kind of a critical thing to be able to do with CAD if you want to be able to update your HyperX analysis inputs to match what you see in the CAD model. Another quick example, maybe you have a plugin or something that does analysis of cutouts and, say, a rib, for example. Go in and measure the diameter of these cutouts. And then another example, we see those, you can kind of see it, the pad up in the skin around the foot of that rib. You could go in and measure that. Maybe you need to update your zoning in the FEM to match that pad up. And the next one we'll show here is getting the geometry out of this the blue spar there. So there's a couple ways you can do that we've added. You can do an intersect, extract a profile from a solid body or from a surface, either or, and drop measurements on that. Another useful feature in that area is doing a split, so you can just slice through the spar, and that plane, by the way, is normal to the direction of the spar. So once you've sliced it, you can go in and use that measuring tool again and drop measurements on it. Obviously, we have a lot of capability in HyperX to do analysis here. So, for example, maybe your spar spacing has been kind of locked in by the CAD designer, and you are now interested in getting what's the optimum thickness on that spar for the given spacing. Go in and open up your cap design property, enter in that 2 inches that you've measured off the CAD model, and rerun your sizing. So changing gears a little bit, now we'll talk about CAD generation in HyperX. Anyone who was at the last users conference would have seen sort of our initial implementation of this. So this is all about, now we're shifting gears to trying to get design data out of HyperX. So here I'm showing panel optimization on that same UAM wing model that Craig had up earlier. We're optimizing the skin of the wing box for a composite hat stiffen design. And that's the sizing just ran for that. And it's showing the sizing results for that zone right there. A few ways you could look at that. The 2D viewer on the right-hand side, which also has the plies in it. You can pull up the table of dimensions, and then I'm showing the margins of safety for that zone as well. So we now have a sizing result that we're happy with, at least for now, and maybe thinking about, let's go to the next step and start trying to understand how those stiffeners, and these are smeared panels, I should have mentioned, by the way. This capability also works for discrete panels if you have those. But here, with smeared panels, we're trying to understand those stiffeners. How do they potentially interact with other structure in the wing? So the utility that just ran generated that CAD stiffener geometry. Each of those is a CAD solid body, and they were just generated by sweeping the optimized profile along those reddish-colored guide curves on the structure. So for each zone, there's a kind of unique CAD profile that matches the optimized design result. And so now we're trying to understand, like I said, how does this potentially interact with the structure that I've imported from my CAD file? So we're just kind of painting down the wing here, looking for issues. Obviously, one thing we notice, we'll need mouse holes in the ribs for the stiffeners. But another thing we notice here, right at the stiffener foot, we've got this kind of clash. What looked like a pretty good stiffener placement actually butts up right up against the edge of a spar. So we need to think about, now that we've recognized this, instead of having to iterate with the CAD designer to sort of figure out this conflict, we can do it all here within HyperX. So what we might try doing is reducing the number of stiffeners. You can see there's fewer guide curves there now, four stiffeners as opposed to 7. So we rerun the sizing, get an updated stiffener geometry, and the stiffeners are a little bit taller because there's fewer of them. But we've moved the stiffeners away from the edges of the zone, and we'll again turn on that detailed CAD geometry and kind of inspect for conflicts. And here we've kind of resolved that issue. We have a nice little gap there now between the foot of the stiffener and the flange of the spar. So we've got to now have a design that we are pretty happy with, and we're ready to hand it over to a CAD person and let them fuss over it. So we'll be doing a CAD export. Before we do that, I mentioned earlier adding metadata to the export. The new feature here is that you can basically any data that you can plot via the legend and labels in the HyperX interface. This can be exported into either a Siemens JT file or a step file. So here I've added a bunch of geometry information to those labels. I'll zoom in a second here so you can see a bit more clearly. So we've got some geometry information, heights and widths and those kinds of things. And then another piece of data we've added on is a PLM part number. And that's something that you could store as custom data in HyperX, and then when you do the export, the CAD person, when they pull that file in, they can immediately see that part number and know which part of the structure they should be working on. What part of the structure is that stiffener thing associated with. So now we're jumping over to NXCAD and thinking from the mindset of a CAD designer, how would they now consume this data from HyperX? So we've got our stiffener geometry, obviously, and then we're zooming in a little bit here, and we have our annotations showing up as well. And there's just a nice side-by-side showing the three pieces here: stiffeners, the stiffener geometry, the geometry annotations, and then the custom data at the top as well. All right, so last step here that, and this is still in CAD designer land. They might need to update their CAD model to reflect this geometry. So I've shown the stiffener geometry being pasted in here. Obviously, we're not intending for that stiffener geometry to be kind of the final CAD part. There's fillets and other things that need to be added. Maybe they even want to sort of start from scratch and just use that as a reference. That's okay too. But they would use that data to update their model. So a couple takeaways from that demonstration. Stress analysts collect the geometry data without relying on CAD designers or software for the import, and then for the export, handoff optimized geometry and metadata in CAD-friendly formats. All right, so we'll shift gears and sort of tell the same story for composites. So still talking digital thread just for composites specifically, and there's obviously some overlap with the CAD topic. So just real quick recap. HyperX does composite optimization. Probably don't need to say too much here. We optimize the laminate stack for each zone. We also generate optimized ply shapes, material selections, and those kinds of things. And that's just a nice snapshot of CAD or of plies in HyperX. Okay, so I've got a quick flow chart to introduce, and then we'll do another demonstration video. So parallel story here. We've got HyperX in the middle, composite import, and composite export. Of course, they're usually kind of switched for composites since HyperX does the initial optimization. So I'll start with the export. We've added some new capability with CAD ply boundary export that I'll touch on in a few minutes. And then another big one is support for the FiberSim HDF5 format. So you can now use that to push and pull composites with FiberSim. And yeah, I've got that over here on the left-hand side too for the import. We supported CATIA for a number of years as well. Just wanted to point that out for the CATIA users in the room. So you could do a XML or a XLS format to exchange with CATIA. And now I'll show a video here. I will be focusing on FiberSim, telling the story with FiberSim since it's the newest edition here. But the workflow is very similar for the CATIA Composites Workbench users in the room. So video starts out with plies on the model in HyperX. Just a quick sort of flip through some of the plies. And then from the top view here, we'll see the ply coverage again. The important thing to note here is that these plies, the coverage is defined as a function of finite elements. So we need to, the first step is to convert this data into something that a CAD or CAM software can understand. So that's the first thing that's showed here. We have a tool that will generate boundary curves around the perimeter of the ply. And then a new addition is we're sticking metadata for each ply, things like the orientation and the material in the name of the boundary curve, so that when you push that out to your CAD tool, the CAD person will see that metadata and understand what they're looking at. And then the other area, of course, the newer, larger addition is the support for the Siemens FiberSim HDF5 or H5 format for short. We've got an export thing here on our ply manager in HyperX, and that just punches out the file. And then quickly, video switching over to NX. So I'll show two sort of parallel things here. The first one is just that import of the boundary curves that I mentioned earlier, just through an IGES or step file. You can consume the plies that way, and then set up your FiberSim model accordingly. And then the second route, which is I think more powerful and direct, is importing that HDF5 format directly. So you can kind of do either or, but I think the H5 is preferred. When you import it, you get the full ply stack in FiberSim. So it's everything the FiberSim person needs that you can hand off to them from HyperX. And then along with that comes the boundaries of all those plies as well, which we'll see. pop up here in a second. So it's gonna, that H5 file has the, the full ply definition, everything the FiberSim user needs to hit the ground running with their draping analysis and all of that. And here's just a nice side-by-side showing the comparison between the ply shapes, HyperX on top and X on the bottom. We see they all match up, and we feel good about that. So the next step would be for the FiberSim person to take these plies that you've pushed from HyperX and sort of massage them into something that is manufacturable. So they might start off by making small tweaks to the plies, maybe filling in little gaps and things here and there, just making them something that's easier to handle and lay up on the part. And then the other thing they might do with these plies is a draping simulation. That's obviously one of the main selling points of FiberSim, where they're generating information about how the material actually lays up on the surface, showing a 45 ply here, for example. Those blue curves are the fiber paths. And then that operation is performed for all the plies. And then now you're ready to actually push plies back out to HyperX. So you want to send out any changes that were made to the ply coverage as well as the fiber orientations. Now push those back out, hand them off to the HyperX users so they can kind of assess the strength and buckling with the current as manufactured state of the laminate. So the last step here is the import. We've got the ply manager with that import already done, and it's just clicking through the plies that came back from FiberSim. And then another nice side-by-side, so the source FiberSim on the left and HyperX on the right, the same plies in both ply managers in both software, and the same ply coverage. And last thing to show here, another big benefit of the H5 format is it does store the draping information for each ply, so we can import that, and we have infrastructure in HyperX to store all that, basically unique fiber orientations per element, and that can be included in your analysis as well. It's kind of a final check of the as manufactured design. So takeaways from that demonstration, for the export, we automate the tedious documentation. I'm sure anyone who's done composites at some point has had to take screenshots or make drawings of which plies cover which areas of the structure. We're automating all of that away. And for the import, you can quickly assess the strength and buckling of the as manufactured laminate. And I've just got a couple slides to wrap up with here. Sort of a side topic, but related area for design for manufacturing, something we're calling effects of defects. So a similar concept, still sticking with the whole digital thread theme. At the top, we've got our familiar CAD, FEA, and HyperX bubbles. But what I'll talk about here on the next couple of slides is trying to incorporate more manufacturing simulation data, as well as data that's coming from the physical manufacturing process itself. And of course, passing that information to HyperX and trying to incorporate it in the analysis in some form or another. So this was some work that was done under the NASA HyCam project that Craig mentioned a little bit earlier. And it's something we're calling the effects of defects framework. So the general idea is that kind of every OEM has their own ways of handling either composite defects or features or off nominal things, whether it be through knockdowns or some kind of simulation or anything else. So we have this kind of two-step process to provide, like I said, a framework for them to plug in their own defect data, their own analysis methods, and so forth. First step of that is import and mapping. So you can take, assuming you have a location and some kind of featured data, like the size of a wrinkle, the height, or the width, those types of things. Assuming you have those two pieces of information, you can import that into HyperX, map it to the FEM, find out which element in the structure that defect corresponds to. And then once you've done that, the second step is to apply, any custom knockdown curves that you may have, or custom failure analyses or anything else to basically disposition that defect and write a margin to it and figure out how you want to proceed with it. So there are kind of a variety of applications here. You could think of consuming process model data, or maybe in situ scans from your manufacturing process, either automated or manually. You've got someone on the shop floor logging defect locations and then trying to disposition them. There's quite a few different applications here that I would love to go into, but we don't have time. So if you're interested, I've got a separate video that I could share with people as well that goes into more detail. And wrap up slide. Yeah, just some takeaways here. So we've made some substantial progress with the data exchange and integration with CAD tools, namely Siemens NX. We've added a lot of capabilities there. And then new capabilities to interface with CAM tools as well, namely FiberSim, so I showed in the video. And HyperX can now import and export CAD data from virtually any major CAD and CAM tool used by aerospace customers. Idea being is we're trying to empower stress analysts to be more savvy with consuming and querying CAD models. They can also generate CAD geometry from optimized results and hand that off to CAD designers in a much more streamlined way. And that's my last slide. I guess time for maybe one? No. Okay.
With the CAD export on something like an orthogrid, is it possible to just export the metadata on like a hang point at the center of the zone as well?
Yes, yeah, it definitely is. Yeah, we have a point creation feature that will actually drop a CAD point at the zone centroid, and then you can still use that metadata label.
Okay. And is this something that we can set up something with you guys to do a quick tutorial on how to go throughout the entirety of it?
Yeah, absolutely.
Yeah, so it seems like the FEA pre-processing is becoming much more of a digital thread. Parts are linked to the actual FEA mesh. Is that something that y'all plan on implementing in the future because it seems like right now the CAD is separate from the FEM in HyperX. Is that something that y'all plan on implementing maybe?
Yeah, I would say it's something we definitely have ideas on. It's kind of a complicated problem because we're not the originator of either the CAD or the FEM. We're kind of importing them. So figuring out that linking is a challenge, but yeah, it's something we're trying to figure out.
I'm not sure if I missed in the video or not, but can you also import FiberSim data such as fly drop and the overlap region? Generally, you define in FiberSim as a final manufacturing definition, and then it kind of increase certain zones or create new zone technically in HyperX data, right?
Yeah, it was kind of quick. I didn't really zoom in on the details, but if you had sort of staggered your apply drops in FiberSim so that they're not all landing in one place, they're spread out. When you import that into HyperX, it would find the FEM elements that fall within each offset boundary, and it updates the zones automatically accordingly. So if you had enough resolution in your FEM, you would kind of see like strips of elements that correspond to that drop location.
I just want to say fantastic presentation. It's really cool stuff that you guys are doing. I think you hinted on how tedious it is to handle the composites in CAD, and I noticed you said you can export the ply data and then re-import it after the designers have kind of made their tweaks. Is there kind of an automated tool that will throw flags and highlight what changes were made from what you originally analyzed?
Not automated. I would say the best way to do that would be through, you could kind of compare zones and laminates between two projects, maybe like a before and after, but
Sure.
yeah.
That may be a
Good feature idea.
huge value add for customers, yeah. Thank you.
Oh, I guess you touched on guide curves for generating stiffeners. How are those guide curves generated? Did they something we do in HyperX, or does it automatically do it? Can you expound on that?
Yeah, so we do have a parallel curve offset function in HyperX. So that works great if you're planning for your stiffeners to be parallel. If they're tapered, it's not as streamlined of a process currently, but we do have CAD generation tools in HyperX that would let you do that. The ones I showed in the video were tapered and they were generated all within HyperX.
Tangent to that, is it possible for y'all to implement like automatic generation of those guide curves based on the analysis results? So stiffener spacing, I think Paul touched on it a little bit, how, creating those effectively the guide curves for different stiffener spacings is a little, there's some challenges there, but.
Yeah, I would say that's another one that we have some ideas on and would like to address it at some point, but don't yet have a definitive plan to. But
I noticed all your stiffeners are evenly spaced.
yes, a simple example.
Hi, I understand that the software is originated for the aerospace industry, so namely aircraft or rocket type of work. Do you see a potential generalization of the tool that perhaps we can use on the broader term? For example, like something comes in mind, say habitation modules design, as well as maybe some of the more advanced architecture work that can base on what you have there.
Possibly, yeah. Actually, Ryan McLaughlin from our company has a good presentation about bike frames.
Oh,
later on.
great.
And
Cool.
So
Thank you.
We do have a few non-aerospace applications.
Sweet.
Thank you.